So it's just doing this slow change through space, taking its time, taking years to do it. It's fine. This one, New Horizon, is the fastest object we've ever launched, fastest thing we've ever made by far. It's going out to Pluto. It's 2015 or 16, something like that. It'll arrive at Pluto. But it took about 7 years. It'll take about 7 years to get there. And all it did was actually just get launched by a rocket. So no engine really whatsoever. It just got launched by a rocket as fast as possible. And it's just slingshot away. And then it just stays the same speed, doesn't increase, and it's just going to fly right past Pluto and take pictures. And then it's going to leave the solar system and probably beat Voyager to meet the aliens in 10,000 years. There's other ideas, solar sails, lasers. You can also use a laser instead of a solar pressure. So you could have a giant laser on Earth, point it up in space, and have some kind of reflector or sail to catch it. That's an idea. Oh, this one's so cool. This one's Orion. This propulsion system relies on nuclear bombs. So all you do is drop nuclear bombs out the back of the spaceship and have nuclear explosions. And then the nuclear explosions push you. You have a push rod, and it actually just pushes your spacecraft, put with nuclear explosions. It's pretty cool. It's actually really efficient, but people canceled it because they were worried about nuclear bombs going off and destroying the Earth and stuff.
Wouldn't that be good for a solar sail because the radiation pushes the space?
Yeah, the problem is with a solar sail, it's kind of like a solar sail. You just get pushed by something. But a solar sail is super thin. It's like this really fine material, and it would get totally burned up and destroyed by this. But it's very similar. You have, instead of a solar sail, you have this really strong pusher plate, and you drop bombs out the back, and you have a shock absorber system that's really strong and powerful and get burnt. It's okay to get burned all the time, and it just gets like pushed by the nuclear explosion, but it's shielded and stuff. Yeah?
Has it been considered for use like outside of
yeah.
Earth, like as a...
Oh, absolutely. But people in general are very against any kind of nuclear propulsion. Greenpeace and stuff protests against it. And the reason is because, A, they just are afraid of the word nuclear, basically. And the second reason is more legitimate, which is you have to get it to space. You have to launch it. I don't think anyone cares as much if it's in space. Although I guess if you brought it back, like someone could theoretically use it as a weapon, turn it around and hit the Earth, right? So that's a danger. But the other thing is, if you have a launch failure, if you have an explosion in the atmosphere, when you're launching it the first time, you can get radiation spread over a wide area. And so that's why people are concerned, because there's these fears that if you launch any kind of radioactive material at all, even if it's not nuclear bombs, and it blows up in the atmosphere, it could spread and rain on crops in England and, you know, do a lot of damage, which is more legitimate. So that's the main reason. I don't really think that's a problem. And the fact is, we actually have launched plutonium, but most people don't know about it. A lot of the robots that we've used have radiothermal generators, radioisotope thermal generators, which are little, basically plutonium, and it just uses the decay of plutonium to generate power. So that's how we powered Voyager, Mariner, and most of our long-range spacecraft, because they're too far out for solar power.
Because of, like, I heard like the explosion, like the energy is super high, and if
Yeah.
you use it like as fuel, you use like a quarter of it to like launch the whole like huge rocket into space.
Yeah, absolutely. That's a picture on the left here. I have an antimatter one, actually. But the fact is, antimatter would be the best propellant ever if we could actually make it in large enough quantities where we need it and store it. We have made antimatter. We've made like, I don't know, 10,000 atoms of antimatter or something, right? We don't know how to make it in large quantities, and actually we spend more energy making it when we've made it. It's kind of a science experiment to make it. We can make it in a lab in a particle accelerator, but in such small quantities that you could never actually, I mean, maybe in the future, maybe if we get good at using it, it will be a good power source, but for now, it is totally impractical, even though it does exist. Because we can't store it. It destroys anything that you put it in contact with. I mean, there's ideas about using magnetic fields, but even so, it bounces around so much, it's very hard to control. And so it's dangerous, unstorable, and too expensive. But it's potentially a very good one in the very far future. Yeah. I think what happens is you get something like a really fast, high-energy collision, and then you get something breaking apart into a particle of antimatter and a particle of regular matter, something like that. I'm not a physicist, but that kind of thing, yeah.
How are the regular nuclear propulsion systems coming along? It's like
Yeah.
canceled for many years.
They were canceled for so many years, the nuclear thermal engines. I've heard rumors that they are being researched, but they were very close to a nuclear thermal engine in the 1960s, and there's no technological reason why we shouldn't have one. It would basically just be like a much more efficient chemical rocket. We should have them. And I think the reason they were canceled is mainly due to like fear of nuclear. Like, we don't want nuclear in space. There's actually a treaty, nuclear test ban treaty, that you can't test anything nuclear in space. I don't know if that applies to the engines, but it might. And even if it does, if anyone said, if NASA came along and said, okay, we've got this great new engine, it's a nuclear reactor, people who don't understand are going to get mad and protest and write their Congress people and get it quashed. So that's why we don't have good nuclear. But if you guys go out and design the best nuclear engine, that'd be awesome. Just out of curiosity, what do you think combat in space would be like?
Like your future, or like?
Yeah, no, now or in the next 100 years. I hope it doesn't happen, but it's just an interesting thing to think about because, you know, you see it in Star Wars, you see it in Star Trek, you see it in every science fiction thing, Battlestar Galactica, whatever. And I think it's always portrayed wrong. It's not going to be like that at all. It's not Luke Skywalker in an X-wing or anything like that. Did anyone have any ideas?
Well, like, I don't know what it's going to be like. I think like on Earth, they have something like that.
Yeah, I'm talking about more of the physics, but that's right, yeah.
Well, really, I mean, it might actually look more like Star Wars than I'd say at first, because at this stage, everything's just in orbit and within reach of ASATs, right? So space combat would really be fighters, like air fighters, going up, shooting an ASAT missile into space.
Yeah.
Satellites.
Yeah.
But assuming it's farther out and you can't do that, then I guess it'd be more like you're using missiles at long range and many lasers.
Yes, I think the main point is that things move so fast in space, you can't really have like a human and a fighter like in that kind of context at all. It's going to be really. Do you want to say? Oh. Oh, it's going to be something like really long distance missiles or rail guns or super high velocity projectiles that go many, many, many kilometers per second or something like that. It's all going to be like really long range, no one ever sees each other, that kind of thing. It's just kind of interesting to think about, but it's not going to be at all like any of science fiction. Okay, so orbits. Orbits are all based on conics, which, have you done that in school at all? Circles, ellipses, parabolas, hyperbolas. Okay. Okay, circles, good. Those are pretty basic. So that is a circle. And if you stretch it out, you get an ellipse. And if you stretch it out more, you get a parabola, which is actually just one-sided. And then if you stretch it out more, you get a hyperbola. I think the parabola might go like this or something, and that's why it never comes down. It does, yeah. Okay, so the parabola doesn't close. The parabola is like this, and the hyperbola is like this. So there's 4 different ones. And essentially, this is an orbit. All of these are orbits. And a circle is kind of the standard orbit because it's the normal orbit that you need to circle the Earth. But if you actually increase the velocity, all that happens is it becomes an ellipse. And it gets longer and longer and longer and narrower. And eventually, you turn that ellipse, it stops closing, and it becomes a parabola. Kind of like that. And then a hyperbola is a really open one that doesn't even bend back on itself. And so that's what an orbit is, and that's what you see comets and other bodies following. So if a comet comes back, then it's some kind of ellipse. Like Halley's Comet is on a really long ellipse, right? So it's just like this. And with an orbit, there's a number of laws, but essentially all you have to remember is the closer to, this is one of the foci. So a circle has a focus at the center, and an ellipse has 2 foci. So that's like, so if you have an ellipse like this, it has kind of 2 foci and they diverge. And the more narrow and longer it gets, that's eccentricity it's called, the more eccentricity you get, the further they come apart. And the rule is it sweeps out, an orbit sweeps out equal area and equal time. So what's equal area here? It's getting narrower, 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 narrow. And then it's like, so as you get to this really narrow section closer to the focus, you go faster. So it's like a slingshot. It goes, wraps around really quickly. So this comet is like going very, 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 very slowly, and then kind of zips around really, really quick, right? And so you can use that for a number of things like gravity slingshots and that kind of thing. You can zip around a planet really quickly and change your trajectory if you do like a little bit of a burn, and then you can actually rob a little bit of energy from the planet. So it's all based on that. It's all based on the laws of falling and just changing from one convex section to another. So that's just what I talked about here. Holman transfer. So you change your Earth orbit, so you change that into an ellipse that hits Mars's orbit, and then you change that into another circle. It's just single engine burns that can change ellipses into circles. All that it is how fast you're going. The only thing that determines your orbit is where you are and how fast you're going. That's it. Change your speed, you're in a different orbit automatically already. So you'll just follow a different trajectory and you'll automatically be in that different orbit. That's how an orbit works. So you're just falling, but because orbit's just falling, remember, and because an orbit is just falling, if you're moving faster when you fall, you're going to end up further away, and then you're going to come back when you fall. So all you do is if you're moving slower, you're going to follow this path. And if you're moving faster, you're going to follow this path. So you can be the exact same spot, and the only thing that determines what path you're going to take, a circle or an ellipse, is how fast you're moving. It's the only thing. And you can also do this around planets to get extra speed. It's called a gravity assist. And there's other exotic ways you can do, like mass drivers, which is just getting shot really fast into space. So instead of using a rocket, you can actually just shoot essentially a big gun into space. You could also have a space elevator, which is just, okay, from the surface of the Earth, you have a space station in orbit of Earth, and it has to be over the equator, because it always has to be over the same point on the Earth, right? And all you do is you have a cord between them, and then you can just ride the elevator up and down. Theoretically possible, but very, very hard to build. So that's why we don't have one yet. And you can launch on different types of missions. Sample return is when you bring something back. You can have a rover go to a planet. You can put something in orbit around something, or just shoot by. The New Horizons is a flyby mission where it's just going to shoot by and take pictures.